Hi, this is James Atlas, a senior lecturer in computer science and software engineering at the University of Canterbury. I'm sorry I can't be there in person today, but I have a fever and I couldn't fly, so I hope you're enjoying Hobbiton and the workshop. This talk is titled Protocol and Sensor Software Development for Fracture Healing and presents the AI component of work led by Debbie Monroe in the Department of Mechanical Engineering. Quick shout out to students who helped with the test harness and data collection. The problem we're trying to solve is to know when a bone fracture has fully healed. Right? If you've ever had a bone fracture, you know that it takes a long time, and that particularly knowing when you can resume normal activity is fairly conservative. They'll take an X-ray several months after the fracture and say, "Yep, that's good enough. You can go back to regular activity." What we would like to do is to be more precise in this and to know exactly when that bone is healing. To do so, we can take a setup like you see on the right there, where there's a bone fracture and we've placed a scaffold over it to kind of hold the bones together so that they'll fuse together as it heals. What we're going to do is to place a strain gauge on that fixation device and measure the amount of strain. From previous studies, we know that at the beginning, the amount of strain when a load is placed on the bone is going to be very high on the fixation device at the beginning. And as the bone fuses together, it takes more of the load. And so the strain on the fixation device as the bone heals goes down. All right, our actual problem from a data perspective is that we have no idea what the load applied to the bone is. We only know the amount of strain that we've measured on the device. Our solution to this is to come up with a protocol, which is a series of activities. So we're trying to figure out, given a strain gauge measurement over time, what activity was in particular this sheep doing during that point of time. We do have hopefully a live sheep study later this year. That's kind of why we're using sheep as an example here. But what we'd really like to do is to classify, is this sheep walking from point one to point two, or is it sitting, or is it kneeling, or is it eating, or possibly is it walking quickly at any given point in time using just the strain gauge data itself and no information about the load applied. It's a difficult problem, but essentially it boils down to a general case of a time series classification. So what we will do is to take a one-dimensional time series data where the amplitude is the strain and the time measured on the axis, and then classify that period of the signal as either walking, standing, or some other activity. The difficulties with this is there are many different approaches. And so what we wanted to do first was to test out current machine learning algorithms for this. And so the current best general purpose algorithms involve a nearest neighbor approach where you could record a whole bunch of signals that you know are walking. And so those are sort of your known examples. And then you get a new signal and you compare it to your database and say, what signal is it closest to in terms of the dynamic time warping distance, right? That could give you the ability to say, this signal looks like previous signals that were walking. Right, another approach is to take a signal and turn it into a series of features, or sort of extract the features from it, like say the number of peaks within a given point of time, or the difference between the height of one peak and the valley between it and the next peak, or the length, or sort of the amount of time spent at each of the peaks. Right, these different series features can be placed into a forced classifier and come up with this time series forced classification. Other approaches use one-dimensional convolutional networks, and in general, all of these could be combined into an ensemble approach, which gives a general best state-of-the-art practice right now to use lots of different kinds of feature extraction and ensemble models. So we tried these on our particular experimental setup, which involved using a drill press to simulate a sheep walking or a sheep standing or eating or that kind of thing. And so using that, we would gather about 50 different time series worth of data with the known activity we were simulating, and then train our model on a sub-selection of these and make predictions on the other subset of that data. We used a leave one out cross-fold validation to test using all of our data so that we could come up with accuracy for the different models. Turns out that most of them were between 80 and 85%, so it didn't matter which model we used. And the most difficult had was determining whether it was walking normally or walking quickly. How does this help our initial problem? We know that if we can detect a sheep walking period of time this week and a sheep walking period of time next week, we could average out a benchmark, like let's say the maximum peak values there or the average peak value, and compare it from one week to the next. And if it goes down over time, we know that it's healing. All right, future, we might employ some more sophisticated CNN models where we could take multiple weeks and place them into the same network structure. That gives us the ability to predict better over time and not lose features by extracting them up front. And we plan an ex vivo and in vivo sheep study later this year. All right, any questions, just send them to my address here. Look forward to talking to you later.